So again, a Bernoulli trial is basically a trial with two possible outcomes, either success or failure. And for example, if the outcome of inspecting part is okay or not okay, then we call non-conforming or not okay as success, and the other one as failure, or conforming as failure, which is 0. We have the probability mass function and expected value and variance. And this is for just one basically part. What if we have a sample of parts? Okay, what if we have 10 parts and we want to know what would be the probability of producing 5 non-conforming parts out of these 10? Okay, then we use binomial distributions, and basically it has two parameters. One is P, which is probability of success, and in that case would be probability of producing, for example, a non-conforming item, and N, which is the sample size. So one important, very important actually, assumption here that the Bernoulli trials are independent. For example, if you are producing a part, the quality of this part wouldn't affect the quality of the next or the next after that. One important fact, sum of n independent Bernoulli random variables with probability of P is binomial. And that makes sense. You have one Bernoulli trial, you add another one, another one, and another one, and then it becomes to a binomial process or binomial distribution. Go ahead.
Can you go to the n choose x notation?
Oh, yeah, sure. So that's basically is n factorial, x factorial, n minus x factorial. Sure. Okay. So, and by definition, 0 factorial is what? Is 1. So that's by definition. Okay? Good. We have one example here. It says in a welding process, 10 different points of a battery tab are welded. So we have a battery tab, and there are 10 of them, 10 points. 9, 10. Okay? And each of those weld points are acceptable with probability of 99%. So acceptable with probability of 99%. Okay? The question says the probability of making a battery tab with 6 failed welds. Okay? So what is the probability of producing a battery tab? And 6 out of 10, for example, this is just one example, are failed. So what is this distribution? It's binomial, because each weld is either conforming or non-conforming, failure or a good weld. Okay, each weld point actually. So we want to find probability of x equal to 6. Okay, and x is the number of failed welds, which follows a binomial distribution with n equal to 10. And what is P? 0.01 or 99%? 0.01. Why? Because we are interested in finding the failed welds, and here is the probability of acceptable welds. So probability of failure or failed weld is 1 minus 0.99, which is 0.01. This is our P. Okay? So this is going to be 10 choose 6 and 0.01, 1 minus 0.01, 10 minus 6. That's it. Is it clear? Any question? Okay. So I give you like a couple of minutes to work on part B. What is the probability of making battery tab with at least 2 failed welds? Okay. Exactly. So the key point is word at least. Okay. What we want to calculate here, it says probability of making a battery tab with at least 2 failed welds. So it means probability of x greater than equal 2. So that's at least. Okay, it could be 2, 3, 4, up to 10. So that's one way to basically find the probability. So you need to add up from 2 to 10. Do this summation. Okay? So you need to add up like 8 terms, I think. Or 9 terms. Yep. Exactly. That's another way to do that. It's kind of like simpler way is to do the complement probability, which is probability of 1 minus probability of x less than 2. And we are talking about discrete. So it's probability of x equal to 1 minus probability of x equal to 0. That's it. But they have the same result. They should have the same result. Oops. Any questions? Nope. Okay. So another distribution that is very well known and used in different applications is Poisson distribution. So sometimes what you want to do, you want to formulate the occurrence of some events. Okay, that event could be, let's say, the number of customers enter a department store. Okay, could be basically the number of defects on a surface of a refrigerator. Okay, or it could be the number of typos in a type page. Okay, so in that case, what you do to model the number of events in a desired unit, you use Poisson. One example is number of scratches. That's event. And our desired unit here is the body or surface of one refrigerator. So every time that you see this structure, we likely can use Poisson distribution. Okay? And lambda here, so Poisson distribution has one parameter, which is lambda. And lambda is the average number of events in a unit. Okay? So for example, the problem says, on average, we have 5 scratches on refrigerator, on one refrigerator, on average. So what is the probability of observing 2 in one specific refrigerator? Observing 2 scratches. Okay? So you know the average, but you want to know what is the probability of observing only 2. Then you use Poisson distribution. Does it make sense? Okay? And one very important assumption is your event should be uniformly distributed in the basically unit. Okay? That's basically what we say. For example, if we talk about scratches, so those scratches should be not clustered. Okay, so something like this, oops, that you have some here and some here, you cannot use basically a Poisson distribution. Okay? And one more thing, unit could be time, could be space. Okay, for example, it could be the number of customers that enter a bank in 1 hour. That unit is hour. Could be the number of scratches on one refrigerator. This unit is more a spatial unit. Okay, does it make sense? So unit could be any unit. Go ahead.
Used when it is not.
So there are some assumptions when you drive Poisson distribution. You cannot use this Poisson distribution. There are some other Poisson distributions, some non-homogeneous Poisson distributions that you can use for that cases as well. Okay, this one which is homogeneous, then you cannot because it's based on this assumption. If you take like a stochastic processes, there are some other assumptions and some other like Poisson versions that can handle those as well. Exactly, that's good. So lambda is not going to be constant. Okay. This is the probability mass function, and expected value and variance, as you can see, is the same, equal to lambda. Another interesting fact, if you have some independent random variable, all of them are Poisson. When you add them up, it's going to be again Poisson with n lambda. Okay? Any questions on Poisson distribution? Okay. One example. In a painting shop, on average, there are 5 defects on the body of a painted car. So, what is the probability of finding a painted body with 10 defects? So, as I said before, whenever we want to find the probability of occurrence of one event in a desired unit, we can use Poisson distribution, given the fact that those assumptions are valid. Okay? So let's say what it says here. What is the event? Here is occurrence of defect. What is our unit? One body of a painted car. Okay? So that's why we use basically Poisson distribution. So X is the number of defects in one car. That's important. And I know that X follows a Poisson distribution with lambda equal to what? What is lambda? 5, because it says on average. Okay? Remember the previous slide? Lambda is the average number of events in a unit, also known as rate. Okay, so the first part says what is the probability of observing 10 defects. So I know that that's basically the PMF for Poisson distribution. I had it in the previous slide. If you look at it quickly, you can see. So lambda is 10, so it's going to be 10, 10, 10, 10. Oh, sorry, lambda is 5. Sorry. I think it's lambda to the power of 10. Sorry about that. And lambda is 5. I hope this one is correct. Yeah. Okay? So that's for part A. How about part B? So for part B, it says the probability of finding 10 defects on 2 painted bodies. So what happens here? The same question, the only thing changes is unit. Okay? So we need to basically change lambda and basically find the lambda for the new unit. And it's very simple. We know that lambda for one car is basically what? 5. So for 2 cars would be 10. That's simple. So probability of x equal to 10 everything should be basically based on the new unit. So your lambda is 10. Therefore, that would be the final answer. Okay? Is it clear? So this is new lambda, actually. What is it?
That doesn't give you the same result as if you took your probability
and multiplied by 2?
Yeah.
No, definitely not, because this is not one-to-one function. No, this is not a linear function.
Is the probability of finding 10 total defects across 2 painted bodies?
Exactly, exactly. Not 10 on each. It's 10 across 2. Yeah, exactly. Any other questions?
Page 10 then.
Oh, yeah, sure. So we know that for one car, we have on average 5 defects. Okay? You agree? Because lambda is 5. So I have 5 defects on one car. So if I change it to 2, on average, it's going to be 10. It's sort of like, let me write it down this way. I think it would be better. Say lambda or average defect. Let's call it this way. Average defects is 5 for one car. And what is it for 2 cars? Okay? So it's basically linear interpolation, so it's going to be 10. So that new lambda, this is lambda. And this is called lambda nu. So your lambda nu would be 5 times 2 divided by 1, which is 10. Okay? Does it make sense?
Average number of 10, there being 10 dents in one car.
Exactly. Exactly. On average, there will be 10 on 2 cars, not in 1, on 2 cars. Because when on average you have 5 in 1 car, then you have 10 in 2 cars. Am I right?
10 be interpreted as
10 is the new, basically, new average with the new unit. That's actually a very good question. So your 10 would be 10 number of defects in 2 cars. Exactly. You change the unit as well. Okay? The definition of unit has changed. Good question. Any other questions? So previous lambda was 5 defects in 1 car. This is 10 defects on 2 cars. Any other questions? Good. So let's see. The next distribution is geometric distribution. And it's again a sequence of Bernoulli trials until we see the first success. Okay? So we tried the Bernoulli trial. If it is failure, then again we continue. So the total number of experiments that we have to make to see the first success follows geometric distributions, given the fact that, assuming that basically Bernoulli trials are independent. Okay? In sort of like a quality control example, number of inspected parts until 1 bad part is cut. Okay? Does it make sense? Because success is defined as finding a bad part. This is probability mass function. So, and that makes sense. If you look at the equation, you can see that. So probability of, let's say, x equal to 3 means in the first two, you cannot catch it, okay, which is 2 failures, and the last one you catch it, okay? So it's going to be, for example, probability of x equal to A. It means the first experiment is failure, the second one is failure up to A minus 1. So these are A minus 1. But the last one is success. That's why we have this PMF function. Does it make sense? And this is the expected value and the variance. And so the number of Bernoulli trials between 2 successes also follows a geometric distribution. And this is because of memoryless property. I will talk about memoryless property later. So what I mean by that, if you have experiment, success, okay? Then again, another one until the next success, okay? This follows a geometric, this also follows a geometric distribution, okay? Any questions? Is it clear? Negative binomial. Anybody knows what this is for? If you've seen this in probability before. Nope. Okay. For geometric, so you continue your experiment until the first success. Okay? What if we continue again until the rth success? Okay? For example, instead of stopping when we see basically the first non-conforming part, we continue until we observe the 10th non-conforming parts. Then the whole number of experiment follows a negative binomial distribution. Okay? So again, to model the number of Bernoulli trials until R successes occur. Example, number of inspected parts until the rth non-conforming part is found. Does it make sense? Okay? So it has 2 parameters. One is R, how many successes we are interested in, and P is the probability of success. What is X? X is, anybody? Yeah, Bernoulli trial, but what is X? Is the number of? Here in this case is the number of trials. So the number of trials I need to do until observe R number of successes. Does it make sense? So in this case, let's say if R is equal to 2, and so what is X in this case? R is 2. So I stop here after 2. So 1, 2, 3, 4, 5, 6, 7, 8 number of experiments. So I did 8 experiments until I observed 2 success. Okay? Does it make sense? That follows a negative binomial. Any questions?
The X is the number of pure trials, not successes.
Exactly. R is the number of successes. Okay? So the question is how many experiments you need to do until you observe R successes. Okay? Binomial, however, was the other way around. You know how many experiments you want to do. You want to find the probability of having X successes. So if you look at these two, you will understand what's the difference between these two. Okay? So binomial, maybe it's good to write it down, is number of successes in n Bernoulli trials That's basically binomial. Negative binomial, however, is number of trials to see our successes. Can you see that? So the number of, this is n, by the way. So number of trials n here is given, and your random variable is the number of success. For negative binomial, number of success is the parameter. The random variable is number of experiments. Can you see the difference? Okay. Now question is, what if r is equal to 1? What happens? Exactly. Negative binomial is the same as geometric when r is equal to 1. Okay? So that's basically the PMF of, they have told me don't point my finger over there, so I need to use mouse. That's why sometimes I go there and then come back. So that's negative binomial. As you can see, that's the PMF function. That's the expected value, and that's the variance. If you compare it with geometric, you can see. So we have r here and r here. When r is equal to 1, this is exactly geometric. Okay? That's it. And that's basically a very straightforward relationship between geometric and negative binomial. Sum of r independent geometric variables is negative binomial with r and p. Okay. You remember that welding process question? Now it says, let's say again, a probability of producing a good weld is 0.99. What is the probability of making at least 5 welds until a defective weld is made? Okay, what is this distribution? Geometric, exactly. So we keep producing until one failed weld is produced. Okay, so probability of, so X is the number of manufacturer produced items until the first non-conforming so X follows a geometric distribution with P equal to 0.01. So your probability of X equal to, what is this, 5 is 0.01, 1 minus 0.01 to the power of 4. That's simple. Try to solve the second part. So what is the probability of making the third defective in the fifth battery tap? What is the distribution for that?
Negative binomial.
Negative binomial. That's correct.
Binomial.
Oh, yeah, sure. This was part A. For part B, X follows a negative binomial with R equal to 3 because we want to continue the experiment until the third failure or basically non-conforming weld is made, and your P is equal to 0.01 again. So it says, what if we catch, what is the probability of catching the third failed weld when we are producing the fifth weld? So basically X minus 1, R minus 1. the same basically equation. Let me just go down, make sure that the numbers are right. Yes, the third defective weld, the fifth battery. Yep, that's correct. Go back. The same probability mass function as you can see here. Okay? And this is important. So your X starts from R. That makes sense. So what does it mean in this case? Your X starts from 3. Why? Because in order to have three successes, then you need to at least do 3 experiments. You cannot do like 1 experiment and see 3 successes. So that's why your X starts from R. Does it make sense? Okay? Sure. Part A, yeah. Is it? Oh, is it? Oh, I didn't see that. Very good catch. Yeah, you're right. It says at least, I'm sorry. Let me refine this answer. So I didn't see that part. So it should be, because it says at least, should be greater than equal to 5. So it's basically summation of I from 5 to infinity, P and 1 minus P, I minus 1. That's correct. Okay. Because you can just continue all the way and see no successes. No, that one is different. So that's different. Yeah. The only similarity is they have the same probability of basically non-conforming item, which is 0.99, which is 0.01. Yeah. That previous problem is bounded by. That's why, because it's binomial. Binomial starts from 0 until 10. Okay, but geometric or negative binomial starts from R. In this case, is going to be 1 and continue all the way up to infinity. Okay. So that's one way. Another way, again, is basically complement probability, which is probability of this guy. Oops, sorry. 1 minus probability of X less than 5 or less than equal to 4. That's easier to calculate. That one is also easy to calculate. You need to have, just to remember the geometric series from calculus. So then you can find this probability as well. Because it's greater than 5, it should be less than 5, which is less than equal 4. Okay, so it's basically the right way of writing it is less than 5, which is the same as probability of X less than equal to 4, because it's discrete distribution. Any other questions? Thank you for catching this.
Question on discrete distributions. If you had a binomial, like you had a coin flip or something, the expected value would be, if it was 0 to 1, would be a half. But
yeah, if it is a fair, basically, coin, yeah.
If you were to actually implement that, you would never be able to actually get half.
That's good.
So is there like something that people usually do in practice that kind of denote that the mean is not real?
That's a very good. That's a very good question. So the thing is, so let's say in Bernoulli distribution, when you basically flip a coin, you know that if this is a fair coin, it should be the p should be half, which means with probability of 0.5, you observe tail or basically head. So let's say somebody tells you, I don't know this probability. Okay, can you tell me about some probabilities by getting some sample? So the sample is what? You repeat this experiment n times, and then you see how many basically tail you have observed, then the probability of tail is going to be the number divided by n. Okay? So that number is not necessarily 0.5, But mathematically, we can show that if you continue this experiment, if your n is very large, goes to infinity, mathematically speaking, then that number would be very close to 0.5 if the coin is fair. So,
in an engineering application, sometimes you use the mean to represent the data, right? But in this case, the mean was never going to exist in the data.
So that's also a good point. We will actually learn this stuff in this course. So whenever you do estimation, so you don't know the real p, so what do? You repeat the experiment and estimate p, okay? That estimation is uncertain. That's what you are saying. It's not exactly what you want. It has some basically variance around it. So that's why we said, okay, this is basically estimated for mean, but it has some variance, okay? So let's say for this case, or let's say for mu, which is the mean of a normal process, you estimate it by what? X bar, okay, usually. But we learned that X bar is not one number, it's a distribution. It has some uncertainty. And then we use that uncertainty to, instead of giving just 1 point, giving an interval. And that's called confidence interval. And then you can say, okay, I don't know what is exact value of mu, but I can tell you one interval, which with probability of 95%, the real mu belongs to that. Does it make sense? And we learned this in class, actually. Yeah. Any other questions? Okay. Review of continuous distribution. So we start with exponential distributions. I think you've seen this before. It has one parameter, lambda, and if you can see, as you can see here, when we change lambda, the shape of distributions changed drastically. For example, lambda is very small, is 0.1, then it's almost flat compared to the case when lambda is equal to 2. And this lambda and the Poisson lambda are basically one-to-one. The same thing, okay? It's kind of like a rate. Examples, waiting time of customers or time to failure of a machine. You run a machine, you want to see, or basically you fly with airplane, okay? You want to see when it's going to fail, okay? So time to failure, one of the distributions that they use for modeling time to failure is exponential. That's mean and variance of the exponential distribution, and this is the CDF function, and it has a memoryless property. So what does it mean? It says, the memoryless property says, let's say machine starts working at time 0, and I want, this is A plus B. I want to know the probability of machine working after A plus B hours, okay? But I have a piece of information. What is it? I know that it already has worked for A hours, okay? Then what memoryless property says? It says exponential distribution is memoryless. So forget about that first A and just calculate probability of X greater than B. So as you can see, instead of calculating this conditional probability, which is X greater than A plus B, given X greater than A, okay, we just get rid of A, and we say it is equal to unconditional probability when probability of X greater than B. It means we restart process again right here. Nothing happened before. So this is new 0, and this is going to be B. That's the same thing. It's called memoryless property. And, okay, let me ask you a question. You have a question?
Lambda head of the exponential bracket, negative A lambda.
You mean here?
Yeah.
No, that's the CDF function. You mean if I dropped it? You mean for memoryless? Or you mean if this equation is correct or not? I think it's correct. Because this is CDF function, not PDF. Yeah. It's CDF. Yeah. Okay. Any other questions? Are we good here? So, time to failure of a machine. So, machine keeps running until it fails. Have you seen this distribution before? What is it? Negative binomial or geometric. Yeah, exactly. So exponential distribution is one-to-one correspondent with to basically geometric distribution. Exponential and geometric, yes. And you can see it from basically expected value and variance. It's 1 over lambda. The other one is also 1 over p. Okay? That's an interesting fact. So let me just go over one example. So in a large computer network, time to log on in a system is modeled by exponential distribution with mean with a mean of 0.04 hours. So x is time to log on, follows exponential distribution with mean, which is expected value of x, is equal to 0.04 hours. Is that correct? Yes. And it says, what is the probability of no logons in the next 6 minutes? So this is important to know that both units should be the same. Here is asking in minutes. This is in hours, so we change it to hours as well. Okay? So what does it mean? There are no logons in the next 6 minutes. It means the first logon occurs after 6 minutes. You agree? Which is the same as saying the first logon occurs after 0.01 hours. Okay? Does it make sense? So what should I do? I need to basically integrate the PDF function from 0.1 to infinity. Okay? So the expected value is 0.04. What is lambda? If I go back, you can see the expected value of x is 1 over lambda. In this case, is 1 over 0.04, which is 25. So exponential with lambda equal to 25. Oops. That was a bad math. Lambda equal to 25. Okay? So what I need to do, integrate the PDF function, which is this guy, from 0.1 to infinity. And lambda is 25. I just replace it with 25. At the end of the day, it gives me this guy. Okay? If you do the math, that would be the final answer. Any questions?
Lambda and your mean, just one more time?
Yeah, sure. It's right here. So your expected value, which is the average, is 1 over lambda. Yes, exactly. That lambda is exactly the rate of basically occurrence of one event. In that case, this lambda can be interpreted that on average, 25 logons occur in 1 hour. Okay, again, on average, 25 logons occur in 1 hour. That's why 1 over lambda is basically related to time between logons. Okay? Does it make sense?
So your E of x, your mean,
Is the mean
could change.
time to log on. Yeah, could change.
Change if you change that time span?
Yes, exactly. Exactly. If you change the definition of the unit here, that could change as well.
What function did you integrate?
The exponential function, the PDF, is exactly this one. Yeah, that one is CDF. Okay? This is CDF. I integrated this function, which is PDF.
So if you plot geometric distribution with the same lambda, the shape will be like exactly the same?
They are very close. Actually, I don't know. I mean, what is your basically, do you have any extra credit in problem in your homework this time or not? No? Okay, next time. So that's actually one of the extra credit problems you will see. And I'm telling you. So it's kind of like finding the relationship between geometric distribution and exponential in a asymptotic way. Okay? How they are related. Okay. So the second part of example, I give you 1 minute, and then, because I have 2 minutes, so I give you 1 minute to work on it, and then 1 minute I solve it. So it says, what is the interval of time such that the probability that no logon occurs during this interval is 0.9? So one hint, here you have the number, you are asked for probability. Okay? The second part, it gives you the probability and says what is the what is the number associated with this probability. And the interval, the lower bound of interval is 0. And upper bound is a, so which I want to find. Okay, so I want to find an interval such that the probability of there is no login in this interval is 0.9. Okay, so let's say interval is bounded by 0 and a. So probability of no logon means what? The first logon actually occurs after a. Does it make sense? So it means there is no logon in that interval. So this probability should be what? 0.9. The problem says. This probability is 0.9. Then it says, what is a? And that's very simple because I integrate basically, again, same PDF from a to infinity. And this probability should be 0.9. So if you do the math, at the end of the day, it would be this guy. This is 0.9. What is the next step? Taking natural log. So if you do natural log, and your a at the end of the day would be ln of 0.9 divided by minus 25. And by the way, this is a positive number because exponential distribution is always positive number. This is negative, then a would be positive. Go ahead.
For the first part, you took your R or your lambda and found your mean, I'm guessing?
No. So the problem says for the first part, you can see the problem says mean is given, 0.04. I use that one and the relationship between mean and lambda to find lambda. Okay? So mean is given, and then based on that, I found what lambda is. Okay? It's not the other way around. Okay? So mean is given, and then I found what lambda is. And I use that lambda for that probability. Okay? Any other questions? See you on Wednesday. Oh, by the way, Wednesday is the due for the first homework. Don't forget that.